Hello, good morning. Let us have some example problems. There are requests for most of the students to do example problems using the kinematics equation and graph matching. Okay? Okay, so let's have these kinematic equation and motion in one dimension sample problems. Number one, let's say you've noticed the sound of a thunder. And then you heard this from your location after 2 seconds when you saw the lightning. So here, if the speed of sound is 340 meters per second, how far is the lightning from your location? In solving problems, first you have to visualize the problem. So here I have some visualizations of of the problem. So let's say you've heard the thunder, and then after 2 seconds, so let's say this is your thunder. Then, after 2 seconds, of course, the sound will travel. It's very fast, but it takes a little bit more time as compared to the lightning. We know that the speed of light is about 3 times 10 to the 8 meter per second. And the speed of sound in air, let's just call it V, is about 340 meter. The SI unit is meter per second. Okay, so now the question is, how far is the lightning from your location? What is your X here? Okay, so it's from whatever this location is, should be a straight line, to your location. So how far are you from the location of the thunder? It's supposed to be this way, but I just draw it like horizontal. But we know, you visualize already. We are looking for the distance. And here, another given is the time. So we write the given variables here. So what are the given? The time is 2 seconds. The speed of sound is 340 meter per second. What else do we have? So what is the x? What is this? Okay, so for our solution, we know that the formula for average velocity is delta x over delta t. So you can always assume here that x minus x naught, that's your delta x, and t minus t naught. And of course, we can cancel out this already because we start at the origin, yeah, and then we start at timer. So let's say this is your origin here, okay, where the lightning comes from. So you have here velocity, we'll just change notation to v, x over t. So it's simple as that. So what you can do is cross multiply. So you will get an equation that is velocity times time. And then you substitute the values now. X velocity is 340, that's meter per second, times the time, which is 2 seconds. So more or less, your distance away from the thunder, from the lightning, is I think it's 380 meters. So this is your answer here. Okay, so I think that's easy, right? Okay, so let's now proceed to the next problem. Okay, for our second problem here, a fire truck starts to accelerate from rest for 10 seconds. It travels with a final velocity of 70 kilometers per hour. This velocity is maintained for the next 10 seconds. Determine its displacement from the initial resting position up to 10 seconds of motion, and then determine the total displacement after 2 seconds. So this is a little bit complicated problem, but first you have to visualize what is going on. So you have a fire truck, it is accelerating from rest and then gaining final velocity of 70 kilometers per hour, and this is maintained for another 10 seconds. Okay? So here, we've divided the motion of the fire truck into segment. So it started from initial velocity v naught. Of course, you have t naught here. Of course, the initial time. So yeah, you can just call it t naught. Okay, and then it's gaining velocity until it reaches a final velocity, and this velocity is maintained. So it's constant all throughout this segment. So that velocity is constant. Okay, so let me what else do we need to know? Perhaps you can, yeah, we can also write the time. So you have time t naught, you have time t1 here, you have t2 here, and these are 10 seconds, and t2 is also 10 seconds. So the next thing that we can do, perhaps we can graph these motion. We've learned about graphical analysis in my previous video. You can watch that for you to understand the graphs in motion. So let's graph it. So if you're going to analyze this graph, as you can see, perhaps you can use a different color. There are, let's say, two segments here. Okay, we can just call it segment number one and segment number two. Segment number one is where the fire truck is accelerating. So as you can see, the velocity is increasing here. But here, velocity is constant in segment number two. So the question for this problem is, what is the total displacement? So if you're going to analyze here, you have displacement 1 here, you have displacement 2. So perhaps we can label that something like this. So we're now visualizing our motion. And of course, you have x naught here, you have t naught, and then you have the velocity. What else? So the question is, what is the total displacement? And we know that it should be x1 plus x2. And of course, the total time is t1 plus t2. So let's just write the given. So you have two segments here. The given are, let's say for segment number one. For segment number one, the given values are initial velocity is 0. Final velocity is given, that is 70 kilometers per hour, which is, you need to convert this into meters per second. And 1 kilometer is 1,000 meter times, I can do a direct conversion. 1 hour is 360 seconds. And that is, wait, I need to calculate. Okay, so the final velocity in segment 1 is about 19 meter per second in SI unit. So what else do we have here? The time, of course, the time t1 is actually 10 seconds. And of course, we are going to find x1, the displacement number 1. So for our segment number 1, we can solve this. Recall the kinematics equation. I think we can use equation number 1. Use kinematic equation KE number 1. And that, oh no, I think that's not right. Recall your kinematic equations. I think equation number 4. What equation, what do you think? Okay, so recall your kinematics equation. You have V naught, you have V, so yeah, this one has V naught, this one has V, as T. So I think it's equation number 2. Okay, so now we know what equation to use. Remember the kinematics equation, guys. So let's continue. Equation number 2 is x equals 1/2. Let me increase the size of that. Initial velocity plus final velocity times time. We know that initial velocity is 0. So that one is 0. That's now easier. 1/2 times the final velocity times time. So you just have to substitute now. This is x1. x1 is equal to 1/2 times final velocity, 19 meter per second, times the time, which is 10 seconds. So here you can see that you can cancel the second. You will be left with meter. And x1 is equal to, you can use your calculator, 19 times 10, 190 divided by 2, it's 95, right? Am I right? 85. Okay. Okay, so this is our displacement number 1 for the accelerating part. Oops. Okay, so let me box it. That's our first answer. Now for the second question is, okay, determine the total displacement after 20 seconds. So it's the whole run already. So we know this already. We determined that. And now this one. Okay, so let me erase my notations there. So let's continue with for segment number 2. I think this is 95. I just verified it. Earlier, I used my mental calculation. So you always have to double check your answer, make sure you get it correctly. Okay, so this is 95 meters. You can verify that as well. So let's now go to segment number 2. Now for segment number 2, if you're going to analyze your graph, you have velocity here and you have velocity here. So if that is your V naught, this is your V final, they are the same. So here you have the given, you have V naught, which is equal to V, or the final velocity, which is 19 meter per second. You have the time is also, it's also 10 seconds. So, and we want to find x2, the second part. And I think since constant velocity, for our solution here, we use the definition for the average velocity, that's delta x over delta t, which is now reduced to x over t, specifically x2. And then, of course, the time is t2. So this is t2. So velocity is given. Should be like this. And that's equal to x2 over x at t2. So your x2 is v times t2. So just substitute the value now. Our velocity is 19 meter per second times 10 seconds. So you get an answer of x2 equals 190 meter. So now the x total, which is x1 plus x2, let me maximize that. We know from x1 we got 95 meters. For x2 is 190 meters. So our final is 285. I might made a mistake. I think that's correct. 285 meters. Okay, again, you can always verify this, and if I made a mistake, apologies, and you can write in the comment, but I think this is correct. Okay, so we're done with our sample problem number 2, and I think we're doing fine here. So now let's proceed to sample number 3. See, here I have a real life data gathering, real life sample of the speed of an elevator. So the elevator is going down. I will not tell you which part. So, but from the graph, I think you can see that the altitude is increasing here. And then something's happening here. What is going on there? And something's happening here. And oops, something happening here and also here. So there are a lot of segments. But in this problem, the question is, okay, given the map of the elevator below, going up and down, determine its velocity going up and down. So how do we determine the velocity? Let's say you are given with this map only. Let's not bother about this yet. Okay, so let's just look at the position time graph. or the height or the altitude. Okay, so let us recall. Hmm, okay, so how do we determine the average velocity going up? So let us recall, I actually already did some analysis here. I further subdivide this already. Okay, this, let's say this is 10, 20, 30, 40, not to scale. I think it can be 10, 20, 30, still not good. You can use a ruler for this, 10, 20, 30, 40, more or less, that's better. So now if you're going to analyze this, to determine the velocity, given with this position time graph, to determine the velocity, what do you get? You need to determine the slope. So we have different segments here, but here it's just determine the velocity going up and down. So perhaps you can just determine the velocity here and determine the velocity here. How do you determine the velocity in a position time graph? Think about it. The slope, right? The slope is equal to the velocity. So the slope here is delta x over delta t. So if this is your segment, okay, if that is your segment, let's say this one and let's say that part, and also we can consider this as well, something like that and something like this. I already made some approximations here because I have the actual data, so I can actually determine that. So the average velocity is that change of x, so the x here and the x here, yeah, and of course the time. So I was able to get v equals average velocity equals, I think it's about the x is about 76 minus 15 over 43 minus 18, something like that. Actually, this is a little bit here. So the the average velocity going up is about 2.55 meter per second. And going down, I was able to determine as well. Okay, so take note, going up now, going up. Take note, 2.55 meter per second. If you're going to look at this, it's basically close to that. We're going to look at the velocity time graph. It is accelerating here, and now it's having more or less a constant velocity. Not perfect, but almost. But here you can see that if this is 1, this is like 3, it's about 2.5 something. It's about 2.5. So more or less our calculations are correct. Okay? So it's not accurate, by the way, yes, not accurate. I did not show you the exact value, but I made it. I just want to show you that, you know, you can determine the velocity in a position time graph. Okay, and you can do the same. Average velocity going down, this is going up. Let's say that's going up, this is going down. It's the same formula, delta x over delta t. But this is your x2 here. This is your like initial x or x1. And this is your t2 and this is your okay, t1. What is the direction here? It's going down, so you're going to expect that your average velocity is negative, and I actually got a value of around 2.5 meter per second, which is also, if you're going to look at this and this, more or less, this is about 2.5 meter per second, but that is negative. Look at this. This is 0, this is downward negative. So yeah, that's how you analyze your motion from a graph. So this is the data from our elevator experiment. So, okay, if you have questions or clarifications or comment, you can just write it in the chat box or you can type it in the comment section below. So for the next video, let's have some examples for kinematic equation, motion in one dimension along the y-axis, which is basically our free fall. Okay?